Okay, we're going to talk about oil refining. The objectives of this screencast are to compare the use of oil as an energy source and as a chemical feedstock, and also to compare catalytic cracking with thermal cracking and steam cracking. So what exactly is oil? Well, oil is a complex mixture of hydrocarbons, linear alkanes from 1 to 20 carbons in length, also called paraffins. There's cyclic alkanes with one or more rings. You have linear alkenes and dienes, linear alkynes, and cyclic alkenes, all of this making up what we commonly refer to as oil. We use oil for two main things. One is a fuel source, and that's the majority of the oil. And then the other is a starting point or starting material for making new products. One of the reasons why oil is used as a fuel source is that it has a really high enthalpy of combustion. You get a lot of energy when you burn oil. It produces energy at a reasonable rate, meaning it's cost effective. It's relatively cheap, it's easy to store, easy to transport. It is established and accepted technology. There is a shortage of viable alternatives, although I think they're making inroads to that, and the alternatives are expensive, although they're getting more affordable as time goes on. Disadvantages of oil as a source. It is a non-renewable resource. Once it's used, it's gone. There are environmental effects of combustion as oil as a fuel. Number one, greenhouse gases. And then there are acidic gases. And as a chemical feedstock, there's a limited supply. Again, it's that non-renewable. We can't use oil as it comes out of the ground. We have to refine it. First off, to remove impurities, and also to separate it into different components for different uses. Number one, oil refining. Step one is the removal of sulfur. Why do we have to remove sulfur? Because sulfur in oil is a source of acid rain. If we were to burn it, it would make sulfur dioxide, which goes into making acid rain. And sulfur also poisons catalysts that are used in later steps. In the oil, sulfur exists primarily as hydrogen sulfide, H2S. So how do we go and refine it? And first step, removing the sulfur. We combine it with potassium carbonate solution to dissolve this hydrogen sulfide. Okay, so to kind of get it out of that gas phase. Okay, then we have a solution. Then we recover that hydrogen sulfide by reversing this reaction once it's separated from the bulk of the oil. Then we burn that hydrogen sulfide, making that sulfur dioxide. We then react it with water, and it makes elemental sulfur and water as a gas. Again, easily separated. Step two in refining the oil so that we can use it is fractional distillation. What fractional distillation does is it separates different components based on their boiling point. And something called a distillation column is used. These are those big columns that you see if you've ever passed by an oil refinery. They're very tall. And it's called fractional distillation because this is basically a distillation column. And at different points along this piece of equipment, you take out different components. Typically, the heavier molecular mass components are taken off near the bottom of the distillation column, where the lighter ones would be coming off the top. All right, so they decreasing in density and boiling point as you go up the distillation column. And you can see the different things that come off that oil distillation column. What are these different fractions used from these different compounds taken off this distillation column? If the chain has 1 to 4 carbon atoms in it, it's used as a fuel and feedstock for petrochemicals. 5 to 10 carbon atoms, that's your gasoline, fuel for cars and chemical feedstock. 10 to 16, jet fuel and paraffin for heating. 13 to 25 carbon atoms, fuel for diesel engines, power plants, and heating. And then the residue, that's the stuff kind of at the very bottom, oil-fired power stations, polishing waxes, lubricating oils, and bitumen used to surface roads. All right, now we're going to talk about something called cracking. And this is going to look at oil as an energy source and as a chemical feedstock. And this is where we're going to, actually, sorry, that was the last. But we're going to look at catalytic cracking, thermal cracking, and steam cracking. Problem is, with the oil, the supply of desired hydrocarbons from that refining step, from that distillation column, doesn't always match what the demand is. So further refining in the form of cracking increases the hydrocarbons that are most in demand. So breaking larger molecules from oil into smaller ones is part of what cracking does. And here we're breaking a long hydrocarbon into an alkene and an alkane. Okay. It allows us to convert larger hydrocarbons into smaller, and it also cracking tends to produce more branched hydrocarbons. You want more branched ones because they burn more evenly. It's more of a steady burn than a long chain would be. Straight chains tend to auto-ignite in an engine, and that's when you get that knocking, which reduces power. The 3 types of cracking we're going to look at: thermal cracking, steam cracking, and catalytic cracking. In thermal cracking, very long chain alkanes are just heated to high temps. That produces a mixture of shorter chained alkenes, and coke, which is basically carbon. Ethene is one of the products that is obtained from this. Benefits: this process is best for cracking long-chained starting materials. Steam cracking. We're going to heat a mixture of alkanes with 8 carbons or less in the presence of steam. We're going to heat it pretty hot, 1250 to 1400 degrees Celsius. This produces a higher yield of ethene and other lower mass alkenes. It also minimizes the amount of coke produced. This process is best for producing low molar mass alkenes. And then finally we have catalytic cracking. We're going to pass large and intermediate sized alkanes over catalyst at 500 degrees Celsius. It produces a mixture of alkanes, alkenes, and aromatic compounds. Branched alkanes are also produced. Several different catalysts can be used in catalytic cracking: alumina, silica, zeolites, also known as aluminosilicates. All of these have a high surface area, which is what you would be looking for in a catalyst. The benefits to catalytic cracking: these are best for producing chains of moderate length and branched chains. These are for uses in fuels. The catalyst allows you to operate at a lower temperature, and you have more control over the products, so you can kind of direct the reaction a bit more.